Hello everyone, I am Constance from Qedit, and today I will present the future of ZSA. So firstly, what is ZSA? So ZSA is for Zcash shielded assets. It allows any type of asset to be represented on the Zcash blockchain. For instance, NFT. With ZSA, we could issue assets, transfer them, and burn them. What is the current status of ZSA? So ZSA is planned for the next upgrade, NU7. The implementation is completed, almost completed, we could say, because there is still some discussion with ECC about some details of the protocol, but the implementation is completed, and then there will be a review of our implementation by ECC. And after ZSA, we would like to add many new functionalities into Zcash. So firstly, we would like to add asset swap. So what is an asset swap? Here we have two users, Bob and John. Bob would like to send 10 of asset A to John, and John would like to send 5 of asset B to Bob. But Bob would like to be sure that if he sends 10 of asset A to John, he will receive 5 of asset B. And on the contrary, John would like to be sure that if he sends 5 of asset B to Bob, he will receive 10 of asset A. It is why we call that an atomic swap. It is either, we like to have either both of the transaction or none of them. So on this figure, we could see the balance of Bob and John before the atomic swap and after the atomic swap. And we could see that after the atomic swap, Bob has plus 10A and minus 5B. And after the atomic swap, John has plus 10A and minus 5B. So now I will explain how we implement it into ZSA. So we have many different users, Bob, John, and Alice. Bob wants 5B for 10A. John wants 10A for 5B. And Alice wants 3B for 2C. So each possibility, so for instance, Bob wants 5B for 10A, we'll call that a swap order. Inside the swap order, we have what the user wants and also some additional information to create the transaction. And when the user will share those swap orders, they will share them off-chain, so out of Zcash. Once two swap orders are matching, for instance, in this figure, the two first swap orders are matching, we could create a swap bundle. So a swap bundle is the combination of two matching swap orders plus some additional information. And then, when we create a swap bundle, we could send it to the blockchain to really create those transactions. The swap bundle could be created either by Bob or by John or by a matcher. For instance, we could imagine that we have a matcher that will receive all swap orders. He will search matching swap orders and he will create swap bundles from the matching swap orders to send them to the blockchain. Now we'll see more in details what we have inside the swap order. So inside the swap order, on the bottom of the figure, we have the user that would like to give 10 of asset A and receive 5 of asset B. And inside the swap order, we have also what we call an action group. It is all the information to create the transaction. So it is a list of actions. An action is a pair of a spend node and an output node, and some additional information to create the transaction. So for instance, we could see here on the swap order that if we add all spend nodes and then we minus the output node, we will retrieve the 10A that the user would like to give. If we look to the action on asset B, we find the 5B that the user would like to receive. And the last action are for the fees of the transaction on the ZEC. So inside the swap order, we have what the user would like, 5B against 10A. We have all the actions. And then we have some traditional information. So we have the flags, we have the root in the Merkle tree, we have an aggregated proof, we have an additional information, which is a deadline. After this deadline, this expiry I, it is not possible to add this action group into the Zcash, into the Zcash blockchain. And we have one signature for each action to prove that the user is allowed to spend this node. And in addition to the action group, we have also a global binding signature key and a global value balance. So here it is the swap order that a user would have to create to say that he would like to give 10A and receive 5B. Now we could see another user that will create the reverse swap order. So the second user would like to give 5B and receive 10A. It is a similar swap orders with an action group, which contains a list of actions and some additional information, and a global binding signature key and a global value balance. We could see that in this swap order, compared to the first design for ZSA, we had to add the notion of reference node, expiry I, and action group. And to simplify the integration of swap order later, we decided to already integrated all those functionalities into NU7 with our ZSA implementation. So now we have two matching swap orders. And from two matching swap order, we could create a swap bundle. So how we will create a swap bundle from two matching swap orders? So we will just copy-paste the action group of the first swap order without any modification. We will copy-paste the action group of the second swap order without any modification. And then we will create the global value balance of the swap bundle. The global value balance of the swap bundle is equal to the sum of the value balance of each swap order. And finally, we will create the binding signature. And to evaluate the binding signature, first, we have to evaluate the SIG hash of the swap bundle. The SIG hash of the swap bundle is a hash of all information inside the swap bundle. So we will evaluate the SIG hash, and then we have to sign this SIG hash with the binding signature of the swap bundle. And the binding signature of the swap bundle is equal to the sum of the binding signature key of each swap order. So anyone who knows swap order 1 and swap order 2 is able to create the swap bundle and to send it to the blockchain Zcash such that the transaction will be created inside this blockchain. So now I will present the status of atomic swap. So we have already presented the protocol to Zcash. Now we have some discussion with ECC about some details of the protocols, just one or two details to fix before having the final protocol. The protocol is available at the zip format on the Qedit zip repo. So it is publicly available. I think it will be soon integrated into the Zcash zip repository. So the protocol is almost finished, and we have also an early implementation. So when we started to work on atomic swap, we started an implementation in parallel on all Zcash repositories, Orchard, Zebra, LibreZcash, and we try to keep this implementation update with the last version of the protocol. So we have, maybe in this implementation, we have to update some parts about the last discussion with the CC, and there is still some work also on the Zebra part. But we have a first implementation of atomic swap, which is almost finished. Now I will present a second functionality that we would like at Qedit to add into Zcash. It is hash time lock contract, HTLC. HTLC, the main application of HTLC are cross-chain atomic swap, payment channels, and there are also many other applications of HTLC. Firstly, I will recall what is an HTLC. So now we have three users, Alice, Bob, and John. Alice will create the HTLC contract by sending 50 of asset A into the contract. And she will define who and how we could spend those 50A. Either Bob could spend the 50A if you know a pre-image of this digest. So if you know numbers such as the hash of this number is equal to the digest. The digest is defined by Alice when she creates the HTLC contract. Or either John could spend the 50A if we are after a deadline. So if an expiry block has passed. And the expiry block here is also defined by Alice when she will create the HTLC contract. And we cannot double spend the contract. It means that if Bob spends the 50A, John will not be able to spend them, even if we are after the deadline. And if John spends the 50A, Bob will not be able to spend the contract. So HTLC is already defined on many blockchains. Most big blockchains have the HTLC implemented on it. As I said previously, one of the main applications of HTLC is cross-chain atomic swap. So what it is? It is quite similar to the previous swap, but on two different blockchains, blockchain A and blockchain B. So we'll have asset A on blockchain A and asset B on blockchain B. And Alice would like to send 50 of asset A to Bob, and Bob would like to send 10 of asset B to Alice. And as previously, we would like to have an atomic swap. It means that if Alice sends 50 of asset A to Bob, she would like to be sure that she will receive 10 of asset B. And if Bob sends 10 of asset B to Alice, he would like to be sure that he will receive 50 of asset A from Alice. So it is either both of the transactions or none of them. So how we could implement atomic swap, cross-chain atomic swap, with HTLC. So we assume that HTLC is already implemented on both blockchains, blockchain A and blockchain B. First, Alice will choose a random number, which is called the pre-image. She will evaluate the hash of the pre-image to obtain a digest. Then she will create an HTLC contract in which she will send 50 of asset A. And she will define how we could spend this HTLC contract. We could either spend it, Bob could spend it if you know a pre-image of this digest, or Alice could spend this HTLC contract if we are after the deadline. I just forget to say that Alice and Bob will agree off-chain about the amount of the transaction, 50A, 10B, and they will share their public keys on blockchain A and blockchain B off-chain. Then Bob will listen to blockchain A, to all transactions inside the blockchain A, and he will see the HTLC contract created by Alice. He will check all the parameters, the amount, 50 of asset A, and the fact that he could unlock this transaction, this contract, if you know a pre-image of a digest. So he will know the digest, and he will check also the deadline here. If the contract is created with the correct parameters, he will create a similar HTLC contract on blockchain B. So inside this contract, he will send 10 of asset B, and he will say that either Alice could unlock the contract if she knows a pre-image of the digest, or Bob could unlock the contract if we are after a deadline. The digest here in the both HTLC contract are the same, and they are the same as the digest that have been selected by Alice. On the second HTLC contract, is sent to the blockchain. Alice will be able to unlock it, so to spend the 10 of asset B, because she knows a pre-image of this digest. She decided the digest, so she knows a pre-image. When she will spend this 10 of asset B, she will have to publicly reveal on blockchain B the pre-image. Bob will listen on all transactions on blockchain B, so he will see the pre-image. And with this pre-image, he will be able to unlock the second HTLC contract and to spend the 50 of asset A. So it is how we could create some cross-chain atomic swap from HTLC. Now I will explain how we would like to add HTLC on Zcash. So a transaction in Zcash is a vector of actions. An action is a pair of an input node, the node that we will spend, and an output node, the node that we create. To create an HTLC contract, we will create into Zcash the notion of an HTLC node. An HTLC node is a ZSA node with some additional information: the digest, the expiry block, and Bob and John public addresses. So now I have to explain how I will add all those parameters into the node. So to add some information inside the node, we have to add them inside the node commitment. The node commitment is just a hash of all information that we would like to store inside the node. So here, inside the message to hash, message HTLC, we will add all HTLC parameters, so Bob public address, John public address, the digest of the HTLC, and the expiry I of the HTLC, which correspond to the deadline. Here it is the first option to add all those parameters into the node commitment. Another option would like to be outside of the ZK proof, evaluate a hash of all HTLC parameters, the digest, the expiry I, and Bob and John public addresses, to obtain the HTLC params digest, and then to hash the concatenation of the traditional parameters with the HTLC params digest inside the node commitment. I will not go in details now, but there is a trade-off between privacy and efficiency in these both options. If we take the first option, we will be able later to keep all HTLC parameters private. So the digest, the deadline, Bob and John public addresses. But the cost in the ZK proof will be higher because the message to hash is longer. If we use the second options, it will be we will have to reveal all HTLC parameters publicly, the digest, the expiry block, and Bob and John public addresses. But the cost in the proof will be smaller. We'll have a proof which has a similar cost than the current ZSA proof, so we'll not increase the size of the circuit. So it is just a trade-off between privacy and efficiency. Then we have the proof. So we have two options. We could have two different proofs or the same proof. We could have one proof for action without HTLC node and another proof for action with HTLC nodes. Or we could have just one proof that supports all transaction with or without HTLC nodes. It is also an option in the protocol. So now we have created some HTLC nodes. It's good, but we would like to be able to spend them, and we would like to be able to check that the requirements are checked when we spend an HTLC node. So when we will spend an HTLC node, the action will be signed either by Bob or John. We would like to be able to check that if Bob signs the HTLC node, he knows a pre-image of the digest. And we would like to be sure that if John signs the action, we are after the deadline. So now the signer is not defined by the HTLC node, but is defined by the HTLC node and also by the unlocking method of the HTLC node. Then we have to think about the nullifier. So when we spend a node, we will reveal a nullifier. And this nullifier, the goal of this nullifier is to not be able to double spend this node. So to not be able to double spend this node, we need to have the same nullifier when Bob spends the node or John spends the node. But if we look to the nullifier equation, here we have the nullifier deriving key nk, and this nk depends of the signer of the action. So here, in our case, nk is not the same for Bob and John. So if we use this equation, we will be able to double spend the node. So it is not good. We need to replace nk by something else, and we need to replace nk by something which is the same value for Bob and John. So we could use a reference nullifier key which is the same for Bob and John. We could use a nullifier key which is shared between the both. We could use psi. We have many different options. And a last point to think is how we will perform all the additional checks that we introduce with HTLC. So the additional checks are the validity of the preimage. So if Bob spends the HTLC node, we would like to be sure that the hash of the preimage is equal to the digest. We would like to check the expiry block as pass if John spends the HTLC node. And we would like to be sure that the identity of the signer corresponds to the way we spend this node with the digest, because we are after the deadline. For each checks, we have two options. We could either perform the checks inside the consensus rules or inside the ZK proof, inside the circuits. And it is, as previously, it is just a trade-off between privacy and efficiency. If we perform a check inside the consensus rules, for instance, we have to check that the expiry block has passed, we have to reveal publicly to the validator the value of the expiry block. But if we perform the check, if we would like to keep this value expiry block private, we need to perform the check inside the circuit, and the cost on the transaction will be higher than performing the check inside the consensus rules. So it is just where we would like to perform those checks is just a trade-off between privacy and efficiency. Now I will present the status of HTLC. So we have an early design of the protocol. It is mainly two early designs, because we have one design where all HTLC parameters are public, the digest, the deadline, Bob or John public addresses, and with the cost of the transaction which is similar to the ZSA transaction. Or we have another design where all HTLC parameters are private. The digest, the deadline, Bob and John public addresses are private. But the cost to create the transaction and to validate it is higher, because we have to add many checks inside the ZK circuit. And we could also perform some design between the both. It means that, for instance, we would like to have Bob and John private. Public addresses, we would like to keep them private, but to publicly reveal the digest on the deadline. So it is just, we could do what we want about which parameter we would like to keep private, which parameter we would like to keep public. And if we keep all parameters private, it will have a cost on the proof creation and verification, but it's possible. So at Qedit, we really would like to work on HTLC after ZSA and asset swap. So then, do you have any question? Okay, so the first questions. Once the protocol is defined and implemented in Zcash, how can this be used in practice? Who decides how much each asset is worth. Who will match the orders? What happens if conflicts needs to be settled? Alors, we have different options. I'll just come back to a slide where we see the different transactions. Here, for instance, here. So I will come back on the swap. A simple example. Here. So here, we have different options. So for instance, we could have two users who discuss off-chain, and they agree off-chain by communication off-chain about their transaction. So they agree that Bob will send 10A to John, and John will send 5B to Bob. Then each user will create his own swap order. He will send the swap order to the other party, to Bob and John. And for instance, Bob will create the swap bundle and publish it into the blockchain. So here we have two users that just discuss between them. Otherwise, we would like also to implement what we call a matcher. And a matcher is an entity that we will receive all swap orders. And if two swap orders matching exactly, it will create the swap bundle and publish it on the Zcash. So the question, who will match the swap orders depends. If this is just a transaction between two users, it is one of the two users that will create the swap bundle and send it on the transaction. Or we could have a matcher that is doing that. And we could have no conflicts because each user just say what he wants. If there is no matching transaction, the swap order will not be pushed into the blockchain, and there is just no transaction. Okay, so there is no more transactions. So thanks a lot for your attention, and bye.